Today we will talk about the n lambda subsets. Earlier in another lesson, we talked about the symmetric n lambda subset. So we've introduced this concept, but we were focusing on the symmetric sectoral structures. Now we want to talk more broadly about those sets. And now you'll see why we want to start with the symmetric, because it makes it easier to understand the broader sets later. So to begin with, let's define an n lambda subset. An n lambda subset is a set of sectoral structures of degree n and order lambda. So for example, if we have the sectoral structure, the complete sectoral set ST4, that includes 6 sectoral structures. Within those, if we want to focus on the ones that have an order of 4, so that will be a 4-4 subset. And it will be made up of only one sectoral structure, and that is the xi structure xi4, or 1 to the 4th subscript 4. So, we will define this structure in this notation, Tu subscript n comma lambda. So anytime you see this, Tu indicates a subset of sectoral structures, and then the n lambda indicates the order, the degree and the order. So Tu subscript n lambda is a subset of Stn, which is the complete sectoral set of degree n. Also notice we've seen earlier that T omega n lambda, omega always indicates symmetry. So T omega n lambda is the symmetric sectoral set, which is of degree n and order lambda. So this is a subset of the TUN lambda. So the symmetric subset is also a subset of the n lambda subset. Sorry, we're saying subset a lot. It might get confusing, but that's why we have this diagram. So the symmetric subset is also a subset of the n lambda. Now, also we know that UN lambda is a subset of the T omega of the T omega n. So T omega n is the set of all symmetric sectoral structures of degree n, and this in turn is a subset of STN. So let's look at it one more time. We have STN, that's the complete sectoral set of degree n. This will make it easier to see. We've got the TUN lambda subset, which are all the structures within this set that have an order of lambda. We have the T omega n, which are all the symmetric structures regardless of their degree. And then at the intersection of these two sets, we have the T omega subscript n lambda. And this in turn is a subset of STN. So this diagram makes it really easy to visualize. Let's go back to our main topic, which are the n lambda subsets. Without focusing on the symmetric component, we're looking at the full subset. So within a set, a complete sectoral set, we can divide that set into several subsets of varying orders. Now, those don't have to be the same size, so it's really, we're not going to really call it a partition per se, but they don't intersect because you can only be of a given order. So for example, if we have a complete sectoral set, then we can divide it into several subsets of varying orders, but the sizes of these subsets are not equal. So we will say that the union of all the n lambda subsets, starting with lambda equals 1 to lambda equals n, gives us the complete set STN. Similarly, we've said earlier that we define the magnitude or the size of a complete sectoral set by the mean function, and we called it mean of n. Now, to define the size of an n lambda subset, we will use the following notation. We will say mean, and then we will put a lambda here, and then we will say of n. So this means the size of the n lambda subset for a defined n and lambda. Let's erase this. So what do we know, or what can we say about the mean lambda numbers? So we will say that mean lambda of n, the sum of all these, the sum of the sizes of all these subsets, starting with lambda equals 1 to lambda equals n, is equal to mean of n, which makes sense. So if you add the sizes of all the subsets, you get mean of n. Notice that if these sets had any intersections between them, then you can't say that. But in this case, we can. And as I said, the size of a TU n lambda subset will be given by mean lambda n. Let's look at a few of these subsets. Let's begin from the start with mean 1 of n. Notice I did not define what n is. But for any sectoral structure, when the order is 1, you only have one sectoral structure within that set. So for example, let's look at the ST5 set. How many sectoral structures of degree 5 can have an order of 1? It's only one sectoral structure, and that is the theta structure, theta 5, or 5 subscript 5. So therefore, we will say that mean 1 of n is always equal to 1. We're also going to start drawing out this triangle where we will have n is the degree and lambda, as we go here, is the order. So we will put 1s all the way on this end for all the order 1 sectoral structures, or sectoral sets, sorry. So all the order 1 sets, regardless of the degree, will have a size of 1. Now let's look at the mean n of n. So this means the sectoral structures that have a degree n and an order of n. And we will see that again for every sectoral structure, it only has, for every sectoral set, only one structure meets that criteria, and that is the Xi structure. So it would be always equal to 1. So there will always be only one structure within a set that meets this criteria. So we're going to put 1s across this diagonal here, or across this edge here, and this corresponds to degree n and order n. Now let's go into some more challenging components. If we look at the meme 2 of n, we will notice that there is a pattern there as well. So meme 2 of n means the set of sectoral structures that have an order of 2 and a degree of n. And this will not be a constant like it is with the order 1. It will depend on n. And what we will notice if we look at a large number of these, or if we try to do a mathematical proof, especially using binary notation, it makes it easier. We will see that the total number of sectoral structures that meet this criteria will always be equal to half of n rounded down. So for n equals 4, you will see that there will be 4 divided by 2 is 2. So there will be only 2 sectoral structures that meet this criteria. And in that case, it will be 2 squared subscript 2 and 3 1 subscript 4 and 3 1 subscript 4. Similarly, we will start by creating this diagonal here based on this rule. But let's look at another type of subsets, which are the meme n minus 1 of n. So that means if n is equal to 5, then we're looking at the sectoral structures of degree 4. And we will notice that, again, the same pattern emerges. We will have a number that is a half of n rounded down. So if we have 7, the degree is 7, and we want to look at the sectoral structures of order 6. At first thought, you might think there are very few, but the way actually to calculate it will be 7 divided by 2 is 3.5 rounded down to 3. So it will be actually only 3 sectoral structures that are degree 7 and order 6. So we notice there's a symmetry starting to emerge here. So meme of noon and meme of n minus 1 are the same. So we also fill out this diagonal line over here. And in fact, there is a symmetry that emerges. And we start noticing that there are always 2 subsets that are symmetric based on their order. Now, let's look at the meme 3 of n. And here the pattern starts becoming more intricate, and we'll just stop at meme 3 of n, because after that it becomes more complicated, and we really need a more generic way to do this calculation. So meme 3 of n is very interesting. It is equal to n minus 1 over 2 rounded down times n minus 1 over 2 rounded up. So that's very interesting that this pattern emerges. So for example, if n is equal to 10, we say 10 minus 1 is 3 in this case. 10 minus 1 is 9 in this case. And we're gonna say 9 over 2 is 4.5. So 4.5 rounded down is 4, rounded up is 5. We multiply 4 by 5, we get 20. And we also see that this is, again, equivalent to meme of n minus 2 subscript of n. Meme of n minus 2 of n. So again, there is a symmetry. And for every one of these, there will be a symmetry. Now, we need a more generic way to do these calculations. So far, we've seen that, we've said it for meme of 1, meme of 2, meme of 3, and then on the other end, meme of n, meme n minus 1, meme n minus 2, and so on. What we find out is that if we want to do a more generic calculation, there are two ways to do it. One, which is really the easier way, but you need a chart or this triangle to use as your guide. If you don't have it, then you have to do it the algebraic way. So this is Losanitch's triangle. This comes up a lot in chemistry, especially organic chemistry, in certain aspects of quantum physics, especially when looking at orbitals. Um, and we see it in a lot of places, especially places where you have a reverse symmetry situation, like we have in many of our sectoral structures. So Losanitch's triangle is really something that recurs in nature a lot, kind of like Pascal's triangle. However, it's not as straightforward as Pascal's triangle. What we notice is that if we start here, if we say this is n equals 1 and this is lambda, we see that there is a clear pattern emerging. That Losanitch's triangle perfectly coincides with the size of an n lambda subset. And that's very fascinating. Because keep in mind, we're talking about these abstract geometric objects, and it's nice to see it coinciding with these naturally occurring triangle. So for, let's say we have a meme of 1, 3. We go down 1, 2, 3, and then there's a 1 here. That's the order. So we know the size is 1. Meme 2, 3 is also 1. Meme 3, 3 is 1. Notice if we add all of these, we get 3. So 3 is really the size of ST3, which is meme of 3. That's the generic meme, not the one with the subscript. Let's look at meme 2 of 4. We'll see 1, 2, 3, 4, 1, 2. So we know that the size, as we calculated it earlier, will be 2. Similarly, let's look at meme 3 of 5. 1, 2, 3, 4, 5, 1, 2, 3. So it is 4. We see that it coincides with the number 4. So 4 is the size of the subset 3, 5, where 3 is the order and 5 is the degree. Now, there is another way to do this calculation, and we're not going really into the proof here. The easiest way to do the proof will be using by converting these sectoral structures into their binary format and trying to do the proof that way, a combinatorial proof. I'll give you the end result here. So meme lambda of n, meme lambda of n is equal to the following. 1/2 of n minus 1 choose lambda. So the basically the combinatorial result we get by doing n minus 1 choose lambda plus n minus 1 choose lambda where q is equal to -1. Remember, q is the quantum binomials. So we saw these earlier when we looked at our symmetric subsets. So we add, and this is very beautiful the way it's done here. So if we think of the regular result as a q equals 1, then this is q equals minus 1. So we have the regular n minus 1 choose lambda plus n minus 1 choose lambda, q is a q of negative 1. We add these two together and we take their, we divide them by 2. You'll see this is really powerful. It's a direct way to calculate the mean lambda of n for any subset of a given degree and a given order. So for example, if I want to know the size of a sectoral subset for degree 100 and order 7, and I can't really use the triangle in this case, I can simply apply this formula. If you look at this formula, it's reminiscent of many uh, things you see in abstract algebra and anything really that has a reverse symmetry or a mirror symmetry. Now let's quickly review. Of course, this one is equal to n minus 1 factorial over lambda factorial times n minus lambda minus 1 factorial. So this is pretty straightforward. Now this one is a little more challenging. This can be simplified into the following, and we can look at why in a second. This can be simplified into n minus 1 over 2 rounded down choose lambda over 2 rounded down. So that way we can simplify it uh, into an easier format, and we can get rid of the negative 1 that is down. What else do we get here? Yes, so there is a catch about this. This formula here, this simplified formula, only applies when either n is odd or when lambda is even. So there is one case where this does not apply. If both n is even and lambda is odd, in that situation, you can't use this formula because it will be equal to 0. So simply that will be equal to 0 in that case. If you want to also simplify this into a different format, like to expand it, just a binomial expansion, we can say that this is equal to this formula here using factorials. So let's quickly go back just to see where we get this from. Remember that n choose lambda for a given q, so for a quantum binomial, as we saw earlier, that means 1 minus q to the n times 1 minus q to the n minus 1, all the way to 1 minus q to the n minus lambda plus 1. All of this is divided by 1 minus q times 1 minus q squared, all the way to 1 minus q to the power of lambda. Now, when q is equal to negative 1, notice what happens here. You have two possibilities. So 1 minus negative 1 to the power of n. If n here is even, this becomes 1. So we say 1 minus 1, we get 0. If n is odd, this becomes positive 1. So 1 plus 1 is equal to 2. So 1 minus 1, 1 minus negative 1 to the n. So you only have two possibilities. It's either a 2 or a 0. And that's why we have these results here, where the result of this term is either 0 or it is factorial expansion we see here. What else can we say about this? There are several properties that emerge from this triangle just by looking at it. There's some interesting um, properties. There's a paper published by Sigel, which is very interesting about the Losanitch triangle and all its properties. We notice that it has some aspects of Pascal's triangle, but not all the time. So for example, we have these areas where 1 plus 1 gives us 2, 1 plus 1 gives us 2. And then we have another 2 plus 2 gives us 4. This is very similar to Pascal's triangle. However, notice this does not add up to 3 like you'd expect it. But again, 2 plus 4 gives us 6. 1 plus 2 gives us 3. So it feels like you have two Pascal triangles merged over a symmetry, but it's really a little more complex than that, and it follows this formula here. More importantly is that this is a naturally occurring triangle in many uh, chemistry and physics applications. So for example, if you do the sectoral structures theory version, if you start counting the subsets of varying sizes without even looking at this formula, you will start filling out the same Losanitch's triangle. Again, the key applications of Losanitch outside of mathematics, a lot of mathematical and combinatorial applications, but outside, you'll see it when you look at isomers, different types of isomers in organic chemistry, certain hydrocarbon chains, for example, and also when you look at molecular orbitals and um, other quantum physics applications. But it's really nice that we have this very visual geometric way to see the triangle. So for example, if you want to figure out um, the degree 7 order 2 structures, all you have to do is imagine these structures and draw out all the possible ones that meet this criteria. So let's actually do it just quickly. So if we want n equals 7 and lambda equals 2, what are the sectoral structures that meet this criteria? So we have, let's begin. We have 6, 1, subscript 7. That's one of them. We have 5, 2, subscript 7. 4, 3, subscript 7. And then are there others? Let's see. Everything else that we will come up with will be a reverse of one of these. So therefore, this must equal to 3.